talking about. It's recording, right?
Yeah.
Talking about. Good.
Yeah.
Said you have an I2C channel.
Clear in this thing. It's clear in the recording. In the TV, it's not good.
Okay. Anyway, still be fine though. So, I was just saying that you basically have anyway. So you have an MCU and you have a secure element, right? And the way they talk to each other is over I2C, right? Then we said this is primarily the master, which is okay, and this is your slave. Yes.
Yeah.
So far, so good. Because in an I2C, this is the I2C bus. The I2C bus is basically what? Two wires. So
Yeah.
two wires?
STA.
STA and STA.
Yeah. Say this is data. This is clock. Okay, with just two wires.
Yeah.
Either way. Anybody asks you anything about a bus, you always say it's a bunch of wires. PCI Express bus, USB bus,
Yeah.
SPI bus, they're all wires. Just a collection of wires. Trying to figure out, how you send electrical pulses over them. When one starts, when one stops, when one goes up, when one goes low, all of that stuff. That's all it is. And I think you've probably done a lot more in electrical engineering, right? That's about it. That's the way I look at it. If I go beyond that and I start reading any of these other data sheets, I'll go mad. So always stick to that point where you're saying that bus, as far as you're concerned, is you might want to learn about how the bus works. There'll be things like clock stretching and all of those pieces. All of those things are important. But the foundational thing about a bus to keep in mind is just a collection of wires that connect a bunch of different things. All right? So anybody who's connected to the bus can probably talk to each other. That's the point. So you have two lines. That's the I2C bus. It's the most simplest one that you will ever find. Simplest peripheral that you will ever find. There's a master, there's a slave. Right?
Yeah.
So far, so good. Now, the question that you guys asked was, what happens when we actually, when the MCU says it can send commands. So it's going to send a command that says generate key pair. At least in this case, assume that this is an ATECC 608A. This is our Atmel microchip secure element.
Yeah.
And the MCU over here is saying send a command. It wants to send this command, which is called the generate key pair. When it sends that command, the slave is simply going to say, okay, generated. Right? Here's the public key. Right?
Yep.
So you get the public key back. Now you pretty much can, store it wherever you want, either in the MCU or what you want to do with it. That's fine. So you send a command, you receive a response. This command can also be something like find this data. Right?
Yeah. Okay.
And this command can also be things like hash this data. Right? Does that make sense?
Yep. Yeah.
So the command can be something like sign this data, hash this data, generate a key pair, and we'll see a bunch of other options as well that you will see. Secure elements, that's effectively what they're used for, right? And I'll also come to the other question that you guys asked me, but you mentioned one of the things that you need to keep in mind is, why do we need a secure element? In the sense, why can't we just use the MCU for something like this? Yeah. Why can't we use the MCU for something like this? That's a question?
Yeah.
So the question is, SCs, or rather secure elements, have a higher bar on security. Means you can go ahead and actually do something like, if you actually go and look at the data sheet for the SC, you will see things like, it's certified against these kind of attacks and those kind of attacks and side channel attacks and all of that. It's been proven to be safe relative to something like this. This piece, it's very, very difficult to mount a number of different attacks. That's very easy on the MCU. Because the MCU is a more complex piece of circuitry. This is a less complex piece of circuitry because it is a fixed function unit. It does only a bunch of different things.
Also maybe because it does not have that many peripherals or that many communication stack.
That's another piece.
Yeah.
Very good point. So here you basically have a bunch of different interfaces. You have more complex circuitry.
Yeah.
You have a number of different components working together. You don't have all that complexity over there. You have a simple circuit that does very specific things, right? These are the specific things that it does.
Yeah.
On top of that, you apply a lot of security best practices, like whatever we've seen in the whatever we've seen in let's say Security Talk or Black Hat or DEF CON or other security conferences where people present their latest and greatest security issues that they've discovered. All of those pieces are taken into consideration when designing it from scratch, right? That's why they get I'll have to look up the certifications, but there's a number of certifications that help you as a user or a buyer figure out whether I should go with this or some other secure element, right? Those are the key points that you need to keep in mind. Making sense about this?
Yeah.
Yes?
Yes.
Okay. Now that that's done, I want to actually talk about one very important thing.
So I have one doubt here.
Yes.
So we're generating a public key. It's one use case of HSM, right? It's not what we're doing here right now.
Yes. So if you're talking about generation of key pair, yes, this is just one command. Depending on why you need your public key, what you're going to do with it, different story. Make sense?
Yeah.
Okay. The rest of the question.
But in the real world, you're going to generate the person who is sending the firmware. He's going to generate the private key, and he's going to give the public key, and we're going to store it in the hardware. We will not generate in the hardware itself.
Yeah. So that's for when we're talking about signing firmware. Like specifically that use case, when you are talking about signing firmware, right? In that use case, you're not actually going to send a command that says generate key pair, and then you're going to get a public key that's generated by this device. No. What we're saying is we will actually have a scenario where, so we will actually have what you call, let's just say we'll have the vendor here. Okay. Some vendor who provides us with some firmware, right? Firmware vendor. We sign this. This is signed by the vendor's key pair. Right?
Yeah.
That is signed by the vendor's key pair. Now, once that is done, the vendor is never going to reveal his private key. That's the whole point.
Yeah.
It stays with him. He wants to put it in a cloud HSM, etc. That's his job. The public key as such is something that this device, assume that this is a device in the field. So this particular device will need, you want to ensure that this device is only going to boot firmware from this vendor. So he's going to sign this firmware, right? You get a signed piece of firmware. Now that firmware is delivered to the MCU.
Yeah.
And this device will have to have the public key corresponding to the private key to verify this piece of firmware.
Yeah.
Now, that public key that's been supplied by somebody like the firmware vendor will need to go on to secure element. Make sense?
Yeah.
So the public keys that are actually present on the secure element are not all generated by it.
Yeah.
Right? They can also be externally procured and inserted into the secure element. Right? But that's not true for private keys.
They will have their individual.
Yeah, it doesn't make sense. Even in some, technically you can do it. You can just call that a public key and put it in there. It's not a thing, it's not stopping you. But generally, when you actually look at the specification from the manufacturer as well, you will never see that they'll say there's no point. Your private key should not be revealed at any point in time. That makes sense to everyone?
Yeah.
The private key should never be revealed at any point in time. That is like the, how do you put this? The number one mantra.
Yeah. For the crypto.
Okay. Cryptography will be broken if your private keys are revealed. People keep talking about breaking the algorithm and stuff. That and all is stuff we'll talk about later. As all relative to this, that is very far-fetched. Okay. This much everybody gets it?
Yeah.
Yes?
Yeah.
Okay. Now from here on, what I'd like to show you guys is, I want to show you very specifically for the ATCC 608A, I would like to show you the layout of I talked about slots, right? Memory slots. I'll show you that in a very graphical view. So that should be fine.
Who is recording that must.
It's showing over here.
Yeah.
All right. Okay, so I was just showing you guys the MCU and the SC, right? This is a much more clearer picture. That too, when it was actually working. You see that the NRF board is the MCU on the left, and the ATCC 608A chip is on the right. You can see there's only like 2 lines for the bus, and there's 2 more for power. Right? Power and ground. That's it. Make sense?
Yeah.
So you just connected the secure element to your board. This is for whatever, to program and test and stuff like that. Now, this is the repo where we actually have what do you say? This is the repo for the secure element driver that I wrote. Okay. It's written fully in Rust. Now we'll go through the details of essentially how this crypto element is actually built or laid out. Yeah? Question? Okay, so let's look at that. So there's examples, etc., a lot of stuff over here, and this is what I want to show you guys. Okay. So here's the part: device personalization. The ATCC 608A is a command-based device which receives commands from the system.
Yeah.
That's what we discussed, and executes those commands, and then returns a result.
Yeah.
If it doesn't understand the command, it's going to return an error code. Just a single byte actually is going to be, right? It contains an integrated EEPROM, right?
Yeah.
Everybody knows what that is.
It's
It's basically non-volatile memory of some sort.
Yeah.
It's called an electrically erasable programmable read-only memory. Okay. So effectively it's a ROM, which means it's read-only memory. It's effectively non-volatile storage. And then it also has its own SRAM buffer and all, which is not very important. But the important piece is the EEPROM. We kept talking about keys being stored, correct? Storing stuff, storing sensitive credentials, etc. That is the place where all of that stuff is stored, the EEPROM. at least according to, at least for the microchip secure element. Okay.
Mhm.
The EEPROM memory contains about 1400 bytes. It's divided into 3 zones. The EEPROM is actually divided into 3 zones. I'm only specifically referring to the ATECC 608A.
Yeah.
It might be different for our NXP, might be different. It might be a little, might be more than different. The architecture itself might be a little different. We'll talk about that. But effectively, for the ATE608A, you have 128 bytes, which is the configuration zone. Now, this is the zone that's important. There's a particular set of bits in the zone. If you set, you lock the device. Once the device is locked, it cannot be, it's an irreversible operation.
Okay.
Okay. That's why it's called the configuration zone. Okay. Then there's the data zone. The data zone is essentially where all of your keys and stuff sits.
Okay. Yeah.
Right?
Yep.
In this case, that's about 1208 bytes, split into 16 general purpose read-only or write-only memory slots. So that's sort of the same thing, right? So if you actually divide 1200 by 16, you'll get, I think you'll get, because we're talking specifically about ECC, right? Your ECC typical key sizes are 64 bytes, public key size. Get it? Yeah?
Yeah.
Same thing. Then you have the OTP zone. The OTP zone is a separate zone, which again has 64 bytes. Now, this OTP zone is a one-time programmable zone. It's a very specific zone in this thing. We'll talk more about that. Before you do anything, you'll need to program the configuration zone first. You'll need to add some values to the configuration zone. And what you see at the bottom, that is the, let's actually look at the diagram. You can see the diagram, right?
Yeah.
This is basically the configuration zone. How many bytes? Configuration zone? 128, right? What is 7C? X7C. Come on, my engineers, my rock stars.
124.
Plus 4.
Yeah.
Right? So this particular zone needs to be programmed first before you do anything. Like before you get down to understanding what's on the device, what's not on the device, etc. First, you need to program the device. And I've color coded the different regions in the configuration zone. Okay. The first, I think, the first 32 bytes, or rather the first 16 bytes, are non-writable. Right? The first 16 bytes are non-writable. Look at the legend towards the left. There's a legend over there? Yes?
32 byte block mark.
Right? So the entire, the 0 to 0C plus 4 is completely non-writable. 32 bytes non-writable. Then you have your I2C address. What is the I2C address? Yes. Right? So every device in this setup that we talk about, when you have an MCU and an SC, you can also have multiple devices on the same bus.
Yeah.
Right? So if that's the case, then you're not simply communicating with one. You would need to have some way of addressing each other. Right? That's why we have addresses that are unique per device that's connected to the bus. And that is what the address is, which is the light green color. Yes? And then, whatever is marked in gray is reserved, not being used at the moment, according to the spec sheet. So all of this is as per the data sheet.
Okay.
All right. Then you have slot configuration. 2 bytes for slot configuration. Slot configuration is even. You basically split what you call the odd and even slots. Okay, so you have 16 slots. According to the manual, you have 16 slots. 16 slots make up 1208 bytes. So each slot, you're basically going to add You're basically going to call it either even or odd. And numbering starts from 0. Okay, so all the yellow stuff is even, all the blue stuff is odd. Then everything else that is again in gray is all reserved for use. Then there's also something called count match and chip mode and all of that. That's all extra stuff, which is not important. There's counter values. Counters are very important. We'll get to that because in cryptographic operations, you need, like, for example, you need to keep a counter of something, right? That's also there. You want a very big counter. That's also there here. Then the important piece is, you see the lock config and the lock value, which I've marked in red.
Yeah.
You set those values and you're pretty much done.
Okay.
Okay.
Yep.
If you set those values to some other value, I'm not talking about the value because you look at them. By the way, the configuration on the left is how I received the chip in the box. Configuration on the right is if you go to microchip and ask them, look, give me a standard configuration for something, they'll give you one like that is like on the right. That is very specifically for their TLS configuration that they're using. Okay. They provide a out of the box configuration that they have. I just sort of contrasted them.
Both are same only, right? That's
Not different. There's
some difference.
there's some
The values are different. Yeah. Okay.
Okay. Right. Then all the keys. The important thing is the key configuration at the bottom from hex 60 to 7C. You see all of that, all of those 2-byte values over there are all per key. In the sense, for each key that you're actually storing, you want certain things to say this is readable, this is not readable, etc., etc. Right? For example, when I generate a pair of keys, the private key is stored over there. By default, the private key is never readable at all. All right. That's what happens. And the bits for that to specify that this is not readable is in the brown A section. That's why it's called key config. Making sense?
Yep. So there are 32 bytes of key config, right? So what does it mean? If every 2 bytes will have config for one key.
No, it's like this. The slot is just a slot. You can put a key in there. You can put anything you want in there. Right? Slot. By the way, when I say I have an EEPROM, I don't have to necessarily only store keys in it. Whatever I deem sensitive, I can store it because if I want that level of protection, right?
Yeah.
So if you're specifically storing keys, you also set these key slots over there, saying this is a key and you can only use it in these cases, in these circumstances like this. So additional options are available for you.
Okay.
Yes. So that's a very simple overview of this thing. Now, if you can just read through the second paragraph over there that I've written. Now, since all of this is pretty long ago, just have to rehash it as well. So the config zone contains values that will determine the access policy for how each data slot will respond. Each of the 16 slots that we have, how will they respond? The config zone will act, whatever we're configuring this config zone with, that will tell us. The configuration zone is the primary thing that can be modified until you lock the device. Until you lock the device, right? Because that's the area that allows you to sort of keep changing stuff in the remaining parts, in the data zone, OTP, etc. But once the configuration zone is locked, everything else is also locked.
Okay.
Yes.
Basically, you're gonna lock the configurations. It is locked. Everything is locked.
128-byte sector. Call it a sector. If you lock it, that's it. So there's nothing else you can do.
The chip is wasted now. If you want to change the public key
You
again.
made an error.
Okay.
Okay, it's not
What if
wasted.
we,
That's the whole point.
Okay.
You lock it because you don't want people to use it, like people to tamper with it, change anything. The moment you lock it, security is now being frozen.
You can access the public key, but you can't change the public key.
Yes. Right. depending on, even if I store a public key, you see those key config slots. If I say the public key should not be accessible, it will not be accessible.
Even public key also we can store in MCU, right? One-time lock if we have there.
Yes, you have OTP fuses in the MCU, you can do that. And that's exactly what people do as well. In the MCU, if you put an OTP and one-time programmable fuse, what happens is it's actually something called physics primarily. You burn the fuse over there, you can no longer edit it, no matter what you do. It's basic physics. You can't change it. So that what they will do is they take the hash of the public key that's used as the device identity and put it in there. So whenever they get a public key, they first take a hash, they compare it with the hash in the fuse. Fuse is only few number of bits. Public key hash is pretty big, 64 bytes you can't have. You take a hash, you get much smaller value. Right? You can put it through. So anyway, so that's that. In order to enable the access policies, the lock value byte must be set. Here's a comparison between out-of-the-box configuration versus some sample configuration that I took from Microchip itself. Okay, that's pretty much it. And here is another example of what is inside the thing. Like what's inside these 15 slots. If you take a look at our pre-provisioned configuration from the Microchip element, you take a look at that. You might be wondering, give me some examples of what each slot is, right? These are the examples. The primary private key is in slot 0. Internal, another private key is in slot 1. Then a bunch of different private keys from 1 to 4. Then a secret key, an IO protection key, secure boot digest key. So many of these options. The slots were particularly configured to hold these type of keys.
Default.
Yeah, in their configuration. You can obviously go ahead and set the right bits for your own purposes. But if you want to get a good start, you can just use this pre-provisioned option.
So in that 128 bytes, oh sorry, not 128, 120, so 1 KB is placed, right? The bigger one.
1208 bytes.
1208 bytes.
In the 1208 bytes, how is that memory sliced up? It's like this.
Okay.
Yes.
Yeah.
Questions on this? Now, I'm not going to go into detailed slot policies because that is very specific to Atmel. Same thing can, so what I'm trying to say is in the NXP's case, in NXP and in specifically in ST safe, it might be the same.
Okay.
It might be exactly the same thing, no difference. Right? There might be a configuration zone, there might be a data zone, and then you sort of control each thing with that. Possible that's how it's built. You need to look at your data sheets. Right?
Yeah.
Any questions on that? Okay, this is all Atmel specific. All right, here's a bunch of other things that I want to talk about. Currently supported commands, which means whatever I've implemented in the driver, right? I can basically send an info command. When I send an info command, it's going to respond saying, I'm an Atmel chip, I have these operations or whatever. It's going to respond with something. That's the info piece. It's also to tell me that, okay, the device is up and running and I'm able to talk to it. If I can get a response for the info command, I'm assured that yes, the device is up and running, it'll accept valid commands. Right? Same thing applies again for lock, read, SHA, write, verify, gen key, sign, nonce. All of these are subcommands that you actually send, sorry, not subcommands, all of these are commands that the MCU can send to, yes. Yes?
Okay.
Yeah.
There's a lot more stuff that I've not added. The SE, you can also send the secure boot command itself. Straight by. There's a full-fledged option for use complete secure boot. In the sense is do the verification, everything, and then give me a response saying that it's secure.
So if you send a secure boot command, where's the bootloader who is using secure boot?
All of that needs to be figured out. That's very specific to Atmel.
Okay.
Okay.
So they have their internal bootloader, which will run a hardware bootloader basically.
No. The chip only does the crypto operations and the storage. They provide a secure boot solution called NRF boot or something like that, like Rust boot. It'll run on the MCU.
Okay.
And will use this particular secure boot option to do the secure booting. Right? That option is there. You have to configure it. That means even we can build the same option feature into secure Rust boot as well.
Okay.
We can have build support for it, but unless we require, we don't want to. By the way, You can see over here some additional things that I was thinking of adding. Random number generation. Very, very important. All right. Then there's key derivation function called KDF. AES, which is for encryption, decryption. That also can be performed on the chip.
So these things we're gonna add in the MCU side. We can't add this in the AC side, right? Because it's a piece of code. Random generation will be a piece of code.
So you just ask for a random number.
Okay. Already we have something.
You ask for a random number. So I'm telling you again, secure elements can have firmware implementations, which means they are running an MCU and they're running their own firmware, but they're just that they are more secure because of all the design and all of that stuff that they put into it. Or they can actually be implemented in hardware and as fixed function units. They can actually be doing that. Either of the cases. But that's all black box to us. We don't care. What's going on inside, we're not bothered. All we want to do is we can ask, we can receive. Okay. So AES and some places also has BES, etc. And here's the C. Basically, I try to mimic whatever is written in C. So I didn't use any extraordinary Rust specific options and stuff. In the sense, the Rust level, the Rust way of coding stuff and understanding. I never used any of that. Basically, I tried to mimic the C API just to see how this thing works. It works brilliantly, very easily, no problem at all. There's a lot of work that can be done on the driver, right? But anyway, here are some of the things that already support. It already supports, which I've already mentioned.
Yeah.
Okay.
So whatever APIs are there here. So if you call those APIs internally, you're gonna call the I2C command. I2C is gonna talk to ISC, return the data.
Yeah. So let's look at an example. So you go into examples folder. You have a bunch of examples that I've already put together. So let's take the simplest one. The info command is what you want to know. Everybody see this?
Yeah.
Bigger. Let's make this a little bigger. All right. So it's very simple. I pull in the HAL, which is the hardware abstraction layer. Then as part of the HAL, there are lots of things like the GPIO, the peripherals, the timer, all of that. I just pull that in. Then I also pull in our important thing. I said the MCU is going to be operating in master mode, right? So if you see over there, there is something called on line number 13, you will see twin, the 2-wire interface in the master mode.
Okay.
Make sense? So I pull that in, then I configure my pins. I say I'm going to use 26 and 27 for clock and data. And I'm going to basically create a new instance of the twin, which is on line 29, right? And there's also something called a delay that I need to provide, which means when I send my command, these are all very dependent on the particular chip that you're working with. When I send my command, I need to wait before I ask for a response, right?
Yeah.
In order to ensure that I wait, I need a timer, right? So I get an access to the timer as well.
In that case, you are running the timer, whatever counted in the data set.
So here's what happens. XU sends a command. SE takes some time to run the command. In usual cases like hashing and all, not even hashing. In usual cases like, say, give me the public key, which we just have to look it up and give it. No, that's not going to take time. Not a lot of time. But in a case where you're actually doing signature verification or hashing a large blob of data, that's going to take time.
Yeah.
Right. So you will have to wait till that processing is done. And then you get a response. So that is something that I have to be aware of, right? Because I need to know when I'm going to when I can expect the answer back, right?
Yeah.
So that is why I'm using a timer. So with just the I2C instance and the timer instance, I create my ATECC 608A driver. It's one instance. It's one type in Rust. I just create a type called ATECC 608A. I just call the type. And then I use that type, which is basically wrapping an I2C instance and a timer and saying, go ahead. Now you can go ahead and set commands. So I'll show you the implementation as well of what's written. See, look at the command example. I am going to send this particular value, line 35. I'm going to send that particular value, and I'm expecting a response. Oh, sorry, wait. I'm actually expecting the response to be this 4 bytes.
Oh, okay.
I'm expecting the response to be these 4 bytes. Because if you actually see, if we actually go back, I don't know if it's here. Perfect. Just open that there. Then open examples. So take a look at this value 00006002, right? Now, if you were to look at the second column, sorry, second row, you see it
00, yeah.
Yes.
Basically, I'm looking for that ID because that's part comes from the factory. It's always going to be that value because this is the third version of the device that was made.
Okay.
And the manufacturer puts it in there. So I'm looking for that. When I send the info command, I'm supposed to get this response back. If I get it, then everything's working fine. Right?
Okay.
That's it. Once this is done, you're assured that yes, you have built a driver that can talk to the device.
Yeah.
Yes?
Yeah.
Yeah.
Then you can also look at other things like, keygen. You want to look at keygen, same thing. You take the peripherals, pin, timer, all of that is the same. Then you say basically, okay, slot 2 is where I want you to generate a key pair. Okay. Oh, by the way, when this thing generates keys, it never stores the public key, it computes the public key. Because ECC, you can derive the public key from the private key.
Mm-hmm.
We know this.
Yes.
Yes, except for Lavanya, everybody else knows this.
Yeah. Yeah.
Right? We'll talk about how that happens. We'll have a separate programming sessions. Anyway, that makes sense?
Yeah.
Yeah.
Okay, so once I select this slot and I say, okay, in this slot, go ahead and run this, do the gen key. I'm going to get the key generation done, and I'm going to basically compare whether the public key that I'm going to comp public key is the computed public key, generated public key is this. Okay?
Yeah.
Comp public key is what I'm trying to do is, this is one request. After I generate it, I will get the public key back. Then the public key that is computed. So what I mean by computed public key, I mean that, let's say you've generated see that line. So when you generated a public key, sorry, when you generated the key pair as such, the private key is present in the slot, right? And you've sort of returned the public, correct?
Yeah.
The next step is, let's say, I don't have the public key. Let's just assume that I don't have the public key because I didn't bother about it. But now I want to get the public key. So if I can send a command saying, give me public key, only public key for the private key in the slot. I can send a command. When I send that command, I will get the public key. So I'm just trying to verify whether both
That you need to specify the slot for this particular. And that's why
so those two are separate commands are going. One is generated gen key command. The other one is get public key command for slot. Making sense?
Yeah.
So we have different slots, right? Like 4-5 slots are there.
Yeah. So in this example, slot 2 is where first I issue gen key. Right?
Okay.
Slot 2 is first where I issue gen key.
Mm-hmm.
Make sense? Then, after I've issued gen key, for some reason I discarded the public key. I don't have it. Let's just assume. Or I didn't ask for the public key to be returned. But after I've done that, after I've generated the key in slot 2, now I'm going to say that I want the public key. I need to know the public key, right? At any given point, I want to know the public key. When I ask for a public key, that is, I send a command saying, give me public key for slot 2. It will compute the public key and return.
Why it will compute? It's already computed, right? In that particular slot, already generated, right?
Private key is there.
Private key. Public key is not. Is that making sense? I hope that's making sense. Take a minute. Let me finish my point. Exactly. The public key is never stored on the device.
Yeah.
The public key is always computed whenever you ask. derived from the private. Right? That's a very good point. Actually, it's derived, not computed. So the private key, there's a generator point G,
Yeah.
dot,
Yes.
public key, sorry, private key gives you public key. Yes?
Yes.
The generators, everybody knows that generator.
Yeah.
Yes?
Yeah.
Okay. That's how you derive your public key. Okay. Anyway, that is basically an example. Now let's look at I'm never going to finish my coffee. What was I saying? Yes. Let's go to the library and look at one last piece. Then you guys can start working on your projects. And I want to know exactly where. So this is basically first thing, my entire driver is just one library. Single library.
Okay.
That's it. Nothing more over there. Just the lib.rs.
Okay.
There's a whole bunch of macros over here. That's fine. But yeah, I have. You'll see why we need this timestamp. It's not very important. But anyway, the important thing over here is the driver. This is my driver. Lines 70 to 80.
Yeah.
I said my driver is what? It's basically a type in which is wrapping an I2C instance, a timer, same thing. Timer again can be delay or another thing. And then I'm also including the address for the device, etc. Just to sort of help me. So this is my driver. Yes?
Yeah.
Making sense?
Yeah.
Now, what I do is I write my implementation of the driver. In the implementation of the driver, you must have an I2C, you must have a delay, you must have a timer. Only then can you build my driver. That's what the generics are saying.
Yeah.
Right?
Yeah.
So once that is done, and look at this, I2C must implement the read trait, the write trait. Delay must implement the delay, whatever, delay millisecond trait. And then timer must implement the countdown rate.
Okay.
Yes?
Yeah.
What I'm saying,
Yeah.
correct? That's the whole Rust part that's coming in.
Yeah.
Now you can't go wrong with this. You can't make stuff that is not conforming to this contract. Yes?
Yep.
Now, once that is done, I'm going to create my instance of a new driver. How do I do it?
Just
Just create a new and
That's it.
Yeah.
That's it.
license.
You saw in the example section, I get my I2C instance, I get my timer instance, I get my delay. I just pass that into the new. I create a new and I just create my instance. I'm done.
Yeah.
That's it. Yes?
Yeah.
Now,
You're passing device address also, yeah.
yes.
Device typing.
Device type is whether this is master slave types, right? Those are all extras. Just because when I was writing this thing, I realized that this is important information that I need as part of the driver, right? Okay. Then there's the wake method. We'll talk about it. There's the idle method. I'll simply explain one method. Everything else will become very simple for you. So let's say when I call the wake method on my driver, what is it going to do? It's going to this byte that is there, 0 byte. One single 0 byte, it's going to write to the bus.
I2C bus.
It's going to write the single 0 byte to the I2C bus.
Mhm.
Making sense?
Yeah.
Line 106. Because I now have an I2C instance, I can do the writing. I'm going to send that byte. I'll send it.
All this is mentioned in the datasheet, like how to wake, how to initialize.
Exactly. This is what took up most of my time. Nothing else took more time than this. The datasheet reading also didn't take because it was somewhere in the datasheet at some footnote. This thing was sort of important. I was working with another person called Emmerich, very, very, very helpful person. He sort of looked at it and he saw it. He said, okay, I think you need to do these things. Then I realized, okay, by the way, he's actually very good with the NRFPs. So he's sort of figured it out.
Okay.
That's the sequence that you need to follow. I need to send a 0 byte, then I need to do something else. There's actually if you look at the send packet, right, there are 2 parts. See this part one and part 2. Those are 2 steps in waking up the device. For the Atmel or for the microchip element, there are two steps. Part 1 and part 2. If I do part 1 and part 2, only then the device wakes up, then I can talk to it. Otherwise, it didn't give me anything. Like there's no response.
It's only for the microchip board, or
This is only for Mac.
Okay.
You'll have to look at the data sheets for other things. What's exactly happening? Yes. Okay. Now, in the send packet command,
Actually, it will hold the line for low. Is the line below?
that needs to happen first.
Okay.
All right, that's what I wrote. That needs to happen. Now, then if you go through the send packet command, it's a little bit of a lengthy block because I sort of put comments, etc. in multiple places. I'm creating the packet, slice 1, slice 2. All of this is me creating the packet. Okay, saying this bytes goes here, these bytes go here, these bytes go here, then put all these bytes together, and then, send command, write it. Makes sense? Write the command. Once the command is written, I'm going to wait for it, which is lines 191, 192, 193, etc. I'm waiting, right? Once I'm done with that, then I get a response. Then I'm going to start matching on the response to see the first byte in the response. Is the first byte in the response what I expect it to be or not? It has to be 0.
Verifying.
The first byte, the first byte holds the length of the response. I'm going to get that. If I get a valid length, fine. Then I'll go forward. Then count byte is equal to this, or count byte is equal to whatever. Depending on that, there are multiple error scenarios that pop up. Then I can choose, whichever option I can. This can actually be turned into a match, which I did not do. It would have been much simpler, right?
Yeah.
This is me when I was starting out, like you guys, always using if-else statements.
Yeah.
Okay. Anyway, so this is a very good place for you to kind of figure out how we're doing things. Now, if you look at the info command implementation, look at this. By the way, info command, this is info, lines 305 to 317. See that? Info command actually calls info base first. What does info base do? Info base actually constructs the command packets. Command packet in this case is bunch of bytes. Correct sequence of bytes, correct command needs to be set. So that construction is what we do. Once that is done, the other part where I spent a little bit of time was calculating something called the checksum. Because the device expects the checksum. It's basically checksum is like a hash, but it's not a hash. CRC. Checksum is nothing but a CRC.
Yeah.
Cyclical redundancy check.
Mm.
Okay, it's basically integrity of data is being checked over there, saying did you send the right command, etc. Anyway, so all of that is done. Once that is done, I send the packet. Then I receive a response. That's it. Yes?
Yeah.
Yep. Okay. Any questions so far? Let's start with that first. Because after this, I want you guys to sort of divide yourself into two groups, and we can start working on the two drivers, NXP as well as. Yeah, we'd like the camera to actually sort of. All right. Any other questions before we end the recording?
Yeah, I had one doubt in that table.
Mhm.
There, yeah.
Yeah, resume again.
Resume. Table?
Yeah. So here there is like 0, 1, 2, 3. All these are like data available on the config thing.
Which one?
Commands.
Commands, right?
No, we're talking about the values.
Value, yeah.
So everything that's on the left-hand side, complete left, is an index. That's the memory of the 128. Address of the 128
yeah.
lines. Whatever's in those fields is actually a value. So for example, if you look at the data sheet, as I said, 4 to 8 is called the revision ID. Right? Like that, in the data sheet, it will clearly mention each sequence of bytes. What does it mean? What should be there? And for the data zone, it does not say what data needs to be there. It just says, if this is a private key slot, mention that this is a private key slot when you're actually sending the command.
Okay.
All right. Then I will fix that this is a private key slot. Nobody can access it.
Okay.
Yeah. Make sense?
And try to say address, like in CC0 is the address.
By the way, you can also, so this particular chip doesn't have SPI. It actually has I2C and single wire, right? It has something called single wire interface.
Yeah.
That's another piece. That's only for this. You guys have, your boards have SPI and I2C. Okay.
It doesn't have.
Right? Fine. All I2C is only. Good job. Yes? Yeah. So, actually happening. The first thing you need to do is what? Connect your MCU to the SC, ensure that the bus and the lines are all correct, and then get to basically wake the board, or rather respond to an info command, whatever is equivalent on your boards. That's all you need to do.
Yeah.
Because everything else comes after that.
Then I just need to do the adjust this.
So you see, one is, that's okay. That's step one. Like you can say that's step 0 or -1. That comes before, where you check to see whether the device exists or not, or you're getting a response or not. That's fine. These devices will not respond if you don't send the right command at all. Like, for example, you just say address check, no, they won't respond. They just won't. You have to send a valid command. You have to send a valid info command to get a response.
Yeah.
Yes?
Yes.
Yeah.
That's the only requirement right now. You don't have to implement the whole thing. You just have to implement I2C driver. That's all you have to implement, which I'm presuming all of you are experts in driver development. Yes?
Yeah.
Who said sort of? I didn't hear you guys. I don't know you if you said that. Okay. All right. So I'm going to pause this. Before that, any questions?
You're calling actually read and write. Those are already there.
Yes. We don't implement any of that. That's the whole point. We just use the HAL. Because the HAL already exists. Now, the only thing we need to know is, what is the command that we need to send? How can we read the command properly?
It is in that reference.
In the manual.
Yeah.
Right? Now, that is the only thing that you're going to spend